Hi, welcome to Orozco's Lectures. I am Jose Orozco, and these are my lectures. This lecture is a Calculus 2 lecture. I hope you enjoy it. This is chapter 9.10, which is Taylor and Maclaurin series. Alright, so first, let's come up with a theorem here. If f is represented by a power series, and recall that the power series would be of the form the summation from 0 to infinity of a sub n times x minus c to the n, right? And here we're centering at c. For all x and an open interval containing c, then a sub n would be equal to the nth derivative evaluated at c over n factorial. And f of x then becomes the series from 0 to infinity of the nth derivative evaluated at c times n factorial times x minus c to the n. Alright, now this should look familiar because in here, that's exactly how we defined Taylor polynomial. I mean, without the series stuff, but in here, this nth derivative stuff, this piece right here, that's how we were defining the Taylor polynomials. So in here, this is actually a Taylor series. And to make it a Maclaurin series, well, we know that in a Maclaurin series, C is 0, right? Because it's centered at 0. So that's the only real difference there. Now, let's do an example. So, example A. In general, I'm going to be focusing more on finding Maclaurin series because, well, Taylor series is just centering it elsewhere. So I'm going to do some of these examples, or all of these examples, as a Maclaurin series. So find the Maclaurin series of the given function. Alright, so let's say that we have f of x is equal to sine of x. Alright. In here, well, I need to figure out some derivatives, right? Because if you recall, when we were doing Taylor polynomials and Maclaurin polynomials, we just started finding some amount of derivatives. So let's figure some derivatives out. So f prime of x, what would that be? Well, actually, you know what? I'm going to start a little bit lower because I do want to have f of x there. All right, so the derivative of sine is cosine. The derivative of cosine, in other words, the second derivative here, is negative sine. The third derivative, it is negative cosine. The fourth derivative, that would be sine. So on and so forth, right? Until we get like to the nth derivative, which would just be, well, it depends how many derivatives we've got in here, right? But it will be some derivative of sine or cosine here. Now, in here, let's see what happens here when we start evaluating these at 0. And I'm evaluating these at 0 because we were doing a Maclaurin series, right? And here c is equal to 0. Yeah. So if I evaluate this at 0, well, what do we get here? Sine of 0 is 0. Cosine of 0 is 1. Negative sine of 0 is 0. Negative cosine of 0 is negative 1. Sine of 0 is 0. So on and so forth. Perhaps I should have done maybe two more terms here. So if I do the fifth derivative, the derivative of sine is cosine, and then cosine of 0 is 1. The sixth derivative, the derivative of cosine, is negative sine, and that gives us 0 when we evaluate this at c is equal to 0, right? So there we go. So now, what do we have here? Well, these right here are going to be the coefficients, right, of our series. And what's the series? The series in general, we know that it's the series from 0 to infinity of a sub n times x. Well, we can write this now as the nth derivative evaluated at c over n factorial times x minus c to the n. But in this case, our center is 0, so we can just have this as x to the n. Okay. Now, let's get some of these terms out. So this would be, well, the 0th derivative. Well, in here that would be f of 0. 0 factorial is 1, x to the 0 is 1. So this plus f prime of 0 times x. Right, I'm just plugging in the values here. So we used to have 1, 0, 1, 2, the second derivative of 0 times x squared over 2 factorial, 3, the third derivative at 0 times x to the third over 3 factorial, so on and so forth. And well, what does that mean here? Well, f of 0 was 0 plus f prime of 0. F prime of 0 was 1, so we have just x plus f double prime of 0 is 0 times x squared over 2 factorial plus third derivative is negative 1, so negative 1 x to the third over 3 factorial. Fourth derivative, 0 times x to the fourth over 4 factorial. Fifth derivative, 1, so 1 times x to the fifth over 5 factorial. Sixth derivative is 0, and I'll go ahead and give you the very next term. It's going to be negative 1 times x to the seventh over 7 factorial, so on and so forth. Now let's notice what happens here. Every other term here is 0, so each one of these go away, and that gives us now that we really have the summation of x minus x cubed over 3 factorial plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial, and I'll just write it as x to the 9 over 9 factorial, so on and so forth, right? And what do we see here? Well, we're alternating in sign. So if I'm going to write this as a series, I'm going to say, well, this is the series starting at 0 to infinity of, well, we're alternating sign, so I'm going to have negative 1 to the n. The other option would have been negative 1 to the n plus 1, but that's when we start with a negative. And here we're starting with a positive, so it's just negative 1 to the n starting at 0. And, well, what does the rest of the series look like? Well, we have x to some power, right? And the power is just a bunch of odd numbers. So the odd numbers can be written as 2n plus 1 when n is starting at 0. And on the bottom, I've got that same odd number, but in factorial. So 2n plus 1 factorial. All right. So that's our series. So what we found here is that sine of x can be rewritten as the series from 0 to infinity of negative 1 to the n times x to the 2n plus 1 over 2n plus 1 factorial. Right? Now, naturally here what we want to ask here is, what is the interval of convergence? What is the radius of convergence? All right. Now at this point, we would normally try to see do different tests here to find the interval of convergence and the radius of convergence, right? But in here, I'm gonna say C9.8 example C. All right, because from there we know that this converges for all real numbers. In other words, the radius of convergence is infinity. All right. So there we go. Now, next example. example B. Let's say that I said find the Maclaurin series for f of x being sine of x squared. Well, luckily here we already know what the Maclaurin series for sine of x is, right? We just found it. Sine of x was that. So from part A, I'll put that in here as a note. From A, we had that sine of x was the series from 0 to infinity of -1 to the n times x to the odd powers, right? 2n plus 1 over 2n plus 1 factorial. So what we can say now is, well, sine of x squared, simply I can do, all I have to do here is replace that x there. So I can say that sine of x squared would be the series from n equals 0 to infinity of -1 to the n times x squared to the 2n plus 1 over 2n plus 1 factorial. And there you go. We're basically done here. If we really wanted to rewrite this in any other way, I mean, I guess you can distribute this 2 in here, make it 4n plus 2, but it doesn't change anything. I will give you an idea of what this looks like, though. This is x squared minus x to the 6th over 3 factorial minus x to the 10th over 5 factorial, right? Is the odd numbers squared. Sorry, this is plus because it's an alternating series. So plus x to the 10 over 5 factorial minus, so this was over 5 factorial, the next one's going to be 7 factorial, so this is to the 14, plus 9 factorial, 8x to the 18, minus so on and so forth, right? So there we go. That was sine of x squared. Cool. Next one. So that was doing it with sine. Now let's do binomial series. All right. So let's find a Maclaurin series for the following. So f of x is equal to 1 plus x to the -1. All right. That's a binomial with the exponent being -1 there, right? This inside here is a binomial. And since we're still doing Maclaurin series, so I'll put that in parentheses. We're doing a Maclaurin series where the center is 0, right? All right. So let's find a bunch of derivatives. So f of x is 1 plus x to the -1. What's f prime of x? That's going to be -1 plus x to the -2. F double prime of x. Well, bring the -2 down, so that's going to be +2 times 1 plus x to the -3. Third derivative, -3 times 2. That's going to be, well, let's write it this way. The negative of 3 times 2 times 1 plus x to the -4. The fourth derivative, what does that give us? Well, I'm going to put this 4 in the front. Negative and negative is a positive, so I have 4 times 3 times 2 times 1 plus x to the -5th. So on and so forth. Right? In this case, we can actually find a nice pattern for the nth derivative, because let's see what's happening here. This 2 is just 2 factorial. This 3 times 2 is 3 factorial. This 4 times 3 times 2, that's 4 factorial. And those are associated with the second derivative, third derivative, fourth derivative. So what we really can say here is we're going to have all of this being n factorial, because it's associated with the nth derivative of 1 plus x to the, well, these exponents are all negative, so it's going to be negative something. And when I had the first derivative, I had a power 2. Second derivative, power 3. Third derivative, power 4. Fourth derivative, power 5. Nth derivative, power of n plus 1. And these were all negative exponents, right? So the negative of n plus 1. And now, since we were doing a Maclaurin series, we have to evaluate this entire thing as 0. So let's see what we get here. When we plug in 0, 1. When we plug in 0, 1. Well, -1, sorry. When we plug in 0, well, this is just 1, but I end up with that 2. When we plug in 0, that negative of 3 factorial. I'm going to write this 2 as just 2 factorial. When we plug in 4, it's positive 4 factorial. In general here, one thing I missed here. Look at this. Positive, negative, positive, negative, positive keeps alternating. So this alternates with respect to whatever variable, whatever n value we have here, right, for the nth derivative. So this is going to be just in general -1 to the n times 1 plus x to the negative n plus 1. And I completely missed the n factorial. Let's fix that. -1 to the n times n factorial times 1 plus x to the negative of n plus 1, right? And now that we have that, oh wait, we were evaluating this as c at 0. So since we're evaluating this as 0, this is just 1 to that power. So you really have -1 to the n times n factorial, which gives us now that our series, well, in general, we know that the Maclaurin series are the nth derivative evaluated as 0 times x to the n over n factorial. In this case, my nth derivative was simply of this format, -1 to the n times n factorial. So I have the series from 0 to infinity of -1 to the n times n factorial times x to the n over n factorial. At that point, we see that the n factorials cancel each other out. So I just have the series of -1 to the n times n factorial, not times n factorial, times x to the n from 0 to infinity. All right. Now in here, this right here is essentially in geometric form, but with an alternating series, right? So we know what the radius of convergence is. So in here, the radius of convergence is 1. In other words, our interval of convergence, because we're centered at 0, is from -1 to 1, not including either of them, right? All right, so in here, this was a binomial series, but it was a very specific binomial series, right? This one was exactly 1 plus, what was it? 1 plus x to the -1. Now, what if it was 1 plus x to any other value, all right? With the exception of positive whole numbers. So let's take a look at that. So I'm going to generalize this example a little bit more. So D. Find the Maclaurin series for f of x is equal to 1 plus x to the k, where k is not a positive whole number. I should say a positive integral. That's all right. Not integral. What? A positive integer. There we go. Nomenclature is important. All right. Where x is not a positive integer. So what does that mean? What we're saying here is, well, first of all, why would we not want it to be a positive integer? Well, let's see. If it was 3, if k were equal to 3, and I'm taking derivatives here, right? When I take derivatives, then I subtract the exponent by 1. So after my first derivative, my exponent is 2. After my next derivative, my exponent is 1. After my next derivative, my exponent is 0. And because of that, we can't take any more derivatives, right? Once I have it to the 0th power, I end up with a constant. and the derivative constant is just 0 forever, forever, and ever. So the thing is, we do not want to deal with that scenario because, well, at some point, you cannot take any more derivatives. But if k was a fraction, for example, let's say that we had it as 5 halves. Well, subtract 1, 3 halves, subtract 1, 1 half, subtract 1, negative 1 half, subtract 1, negative 3 halves, so on and so forth. Notice that you can always keep subtracting 1 on these exponents, right? And it would not become a constant or anything like that, right? And if it was negative, well, we end up with something like what we had here in example C, right, with a negative exponent there. So let's do this more generically for any k. All right. So first, let's start figuring out some derivatives. So we had that f of x was 1 plus x to the k. F prime of x would be, well, bring the exponent down, k times 1 plus x to the k minus 1. Cool. That's the first derivative. The second derivative, I have k times k minus 1 times 1 plus x to the k minus 2. Third derivative, k times k minus 1 times k minus 2 times 1 plus x to the k minus 3. I'll do one more so we can see what the pattern is here. Fourth derivative, k times k minus 1 times k minus 2 times k minus 3 times 1 plus x to the k minus 4. All right. So what would the nth derivative be? Well, in here, notice that, well, in the first derivative, I just have k, right? In the second derivative, k times k minus 1. So I had two terms where the second one I'm subtracting one smaller value than this. In the third derivative, three terms, 3. But the last one that I'm subtracting is minus 2. That's one value less than what the third derivative is there. The nth derivative, what n is. There we go. And the next one, four terms, right? And that last one, the value right there, that 3 is 1 less than the amount of derivatives that we've taken. So the nth derivative here is going to be, well, let's write it as k times k minus 1 times k minus 2 times k minus 3, so on and so forth, up until we get to one value less than that. So I'm going to say k minus one value less than n, so n minus 1, right? And then I have 1 plus x to the, look at this, in the derivatives, we're subtracting the nth derivative, right? In the first derivative, I'm k minus 1. Second derivative, k minus 2. Third derivative, k minus 3. So for the nth derivative, it's k minus n. All right? All right, so now, since we were doing the Maclaurin series here, we need to evaluate all this for c equals 0. And when we do so, well, we have 1 plus 0, that's 1. To the k is 1, so we have 1. In here, this piece right here is just 1, and we have that k. In here, in the second derivative, this right here is just 1, and we're left with k times k minus 1. Similarly here, we're going to have k times k minus 1 times k minus 2. In the next one, k times k minus 1 times k minus 2 times k minus 3. And the last one here, we're going to have, well, I'm just going to go ahead and copy and paste this piece. Right? Ah, look at that, it doesn't fit. Let's make it smaller. Ooh. Close enough. Let's get rid of that and that. Okay. So that's what we get in there. So now, what does that say about our series? Well, our series, since that's the nth derivative, this tells us that f of x, which again was 1 plus x to the k, would be the series, and this is the series from n equals 0 to infinity of, well, the nth derivative evaluated at 0 over n factorial times x to the n, right? Now, what does that mean for this? Well, the nth derivative, we just wrote it to be this thing. So what we have here is going to be the series from 0 to infinity of that thing that I copied and pasted. Look at that. Still there. I like it. Now, and then that's times x to the n over n factorial. Now, what does this look like? Well, in general, this looks like 1 plus kx plus k times k minus 1 over 2 factorial times x squared plus k times k minus 1 times k minus 2 times x to the third over 3 factorial, so on and so forth, right? All right, so that's example D. In here, I will make a note here. The radius of convergence of this is 1. All right, so I'll make that note here. Note, radius of convergence equals 1, which implies, well, that our interval of convergence is from -1 to 1. All right, now, next example, E. Let's say that it's find a Maclaurin series for f of x is equal to the cube root of 1 plus x. All right. Now here's the thing. 1 plus x is what we did here. And here I have it to the k. Well, what would k be here? K would be 1/3. So right away, I can say that, well, this series is going to become, so f of x, well, we already know, well, let me just go ahead and copy and paste this. It's already this thing. And I'll write it here as 1 plus x to the 1/3, and it equals this summation, this series. So we can go ahead and say, well, what does that look like? Right? Well, in here, that 1/3 should be k's, right? So perhaps I'll cross off each of these k's. And in this case, it means 1/3. 1/3 minus 1. 1/3 minus 2. 1/3 minus 3, so on and so forth, right? Until 1/3 minus n minus 1, and this is x to the n, right? So, but I mean, what does that actually mean overall, right? Because this very much depends up to the terms that we've been doing. So we have, I'm going to write this as 1 plus x over 3 minus 2x squared over 3 squared times 2 factorial. And what am I doing here? I'm plugging in 0, right? Because with 0, we just stop at, well, just k itself. We don't really have any of the other terms there. When I plug in 1, we only have up to the first term, right? Of this product, I mean, so on and so forth. When I plug in 2, we have the first 2. When we plug in 3, the first 3, all right? And this keeps going. So we have plus 2 times 5 times x to the third over 3 to the third times 3 factorial. Plus, minus 2 times 5 times 8 times x to the fourth over 4 factorial, so on and so forth. All right, and here these plus and minuses are happening because, well, we end up with a whole bunch of different negative values here when we multiply this out. All right, but essentially here, the point of this example was to say, well, now that we've got this generic idea for 1 plus x to the k, I can do it for any non-positive integer, right? So whether I do it for the 1/3, or we could have applied it to example C as well, where we do it to the -1, right? All right, now that is the end of 9.10. Wasn't that fun? If you think I made a mistake somewhere, you're probably right. Tell me all about it in the comments. If you feel you learned something from me in this video, hit the like button, hit the subscribe button, but more importantly, share it. Share this video with your classmates. And remember, you don't have to like math in order to be good at it. But you do have to be good at it. I am Jose Orozco. Goodbye.